Hello and welcome to this episode of AI GovCast. I'm Sylvia Oakland. And here with me today at the AI+Expo in Washington, D.C. is Cecilia Garraffo, the founder and director of AstroAI Institute, the Center for Astrophysics with Harvard and the Smithsonian Institution. Cecilia, thank you so much for joining us today.
Thank you for having me, Sylvia.
You do a lot of very, very cool work. I'm very excited to talk about all of this. We're talking about AI and we're talking about space, and two of my favorite things. So right off the bat, you created AstroAI, and do you mind kind of explaining to our audience what you do there and the work that you're doing?
Yes, of course. I created AstroAI because there's a huge opportunity and a challenge as well. So we are entering this data revolution in astronomy, and we are going to observe so much at a completely different rate that will mean we're not going to be able to make the most of the data, make discoveries. Discoveries are not going to scale up with the amount of data. So we have to change the way we do discovery, or at least complement the way we do discovery. And the challenge is that AI that can help with big data doesn't really work off the shelf for our data, because our data is very different. Scientific data is different than images and text, for which these AI models that people are familiar with, that work on language and images, are optimized for. So we have to build on our own in a way, of course, using the technology that has came out recently, that keeps coming out of the computer science community.
Right. And so what kinds of use cases then are you looking at within AstroAI? You mentioned that the data is different. It's not using text and images in a way that maybe I or my colleagues are using it for emails or for, just experimenting. So what kind of use cases are you guys looking at with AstroAI?
Yes, so it's not always transferable, the experience of AI that a user can have. I'm not talking only about generative models here. I'm talking about, there's many different uses for many different cases, but let's just take huge data sets. With some AI tools or machine learning tools, we can now, for the first time, intentionally search for the unexpected, for things we don't know are there, for patterns that we are not aware they exist, intentionally. So you cannot do this with traditional software. You have to look for something that you're coding and telling the model how it looks. And so we used to find what we were looking for or discover new things by accident. But now we can say, please find a new class of data that share a pattern, but that is not a pattern that you necessarily know. So just cluster the data according to similarity between them. That is not a similarity that you have to code in. So that is very powerful. We could have discovered so many things with that. Many astronomical images or data have patterns that are very salient, but were overlooked for decades because they're so rare. But now if you see them all together, because you have a model that cluster them, then they wouldn't be over. You're like, oh, what are all these arcs? Oh, those are gravitational lenses. So that's one of the uses. But in general, astronomy is the game we play is an inverse problem. We want to be able to go from an observation and know what were the parameters, physical parameters. Let's say we're looking at a black hole, like an accretion disk of a black hole, and we want to know what is the mass and the spin of the black hole. We want to know the initial parameters and the physics that rule them by having the end product. And so we want to do what we call an inverse problem. Take that data and tell us how we would have to start a simulation if we wanted to get to that scenario. And that's, AI and machine learning are great at that.
Right. And we talked a little bit, too, about how AI and machine learning can help with comparing those data sets, not only finding them, but then comparing them. And I hear that a lot within the science and discovery realm, because there is so much data to look at. And I've heard you speak before in talking about finding life on other planets, whatever type of life that may be, and so how is AI helping with that, with identifying life on another planet that may not even be within our solar system?
Yes, I'm happy to discuss that. And this is just what I'm going to tell you about is applicable to so many other problems in astronomy and in general, right? So when you look at, so there's exoplanets, there's more than 6,000 exoplanets detected and discovered to date. These are planets that orbit a star that is not the sun, so outside the solar system, they're pretty far. And we can now not only detect them, but we can detect molecules on those planets, on the atmospheres. And we do that by looking at the light of the star when it shines through the atmosphere of the planet. And the way that light is absorbed depends on what is the chemical composition of the atmosphere, what molecules are present. Some molecules happen to be byproducts of life, so they indicate life. So what we want to do is, from that observation that we call a spectrum, is like the light separated in different energies, like when you use a prisma. We want to see the absorption lines on those and see, okay, what are the molecules that are absorbing this light? We know for many molecules how they absorb light from the laboratory, or mostly. And so if there was only one molecule, we could tell. Now, if there's two molecules, it's a little harder because there's all these interactions and you have to do it for different temperatures and pressures. So there's more and more combinations that could be possible. If there's 3, 4, how many molecules do you have? How many molecules not only you have in that atmosphere, but you want to probe for? So the more molecules you want to put in your model to be able to retrieve them, the more complicated it gets. And so the limitation there is that we can only do that for very few molecules right now because of the computational cost. Instead, what we have built and we are still working on is, what if we can invert the problem and take the spectrum and extract directly the molecules from the spectrum, instead of comparing how one spectrum in the laboratory will look and then comparing it to the observation. So you can invert the problem and say, okay, these are the combinations that are in there, and these are how much of each molecule is there, and the temperature and the pressure of the atmosphere. And so maybe you heard, like, there's been many claims of having detected life elsewhere in the universe, and those are typically claims of detection of biosignatures, and there's a lot of discussion and controversy every time one of these comes out. And the reason is because to detect one of them, how many did you try, right? There's a limitation. So the more molecules that you can put in your model, the more sure you can be.
Right.
And so right now it's just a few, but we're trying to get that to thousands.
And you said that's because of a computational problem? Okay. Exactly. So then, like, what needs to happen? You know, we've already, I think, made a lot of progress with AI just in the past year. I mean, there are so many new models, there are so many new things coming out, but what within, like, the next year kind of needs to happen for you and your team at AstroAI to maybe take that next big step?
Yeah, no, the computational bottleneck is with the traditional methods. With inverse modeling we're doing with AI, we already can scale that up to thousands of molecules instead of 1 or 2 or 3. Right? We first did it for 5, but we're now working on a computer vision framework that will take us to be able to include thousands of molecules. And so it's not a matter of increasing the computation anymore. It's a matter of building a different kind of model that is based on this new AI technology that can solve inverse problems that we're not able to solve in high dimensions before.
Yeah, so then what is your team looking at next? You guys have kind of the foundation ready to go. Let's say within the next 6 months, within the next from this next 6 months to the next 5 years, where do you kind of see progress being made?
Yeah, so we are working on this, scaling the model that we had for 5 molecules to thousands. I think that will take, we now are working on that, supported by the Sloan Foundation, and that grant is for 3 years. So we have a team that is going to start working now this summer on that. So hopefully in 3 years, we'll have a very good model to do retrieval of of molecules from exoplanet observations. We also it will be very valuable to get the next generation of telescopes in that direction, because then we'll get better signal to noise and less confusion, and they go hand by hand, the hardware and the software advances that we need to be able to make any conclusive remarks.
Yeah, I saw the AstroAI will be hosting a workshop, I believe, in June. Is that correct? Are there any? I saw the close for proposals just happened, but is there anything that you're really looking forward to about the workshop coming up in June?
Yes. This is the third year we have the workshop, and it's been wonderful the last 2 years. It builds a sense of community, networking, opportunities, and we really, really go for starting at engaging people from zero experience with machine learning, scientists that have no previous knowledge of machine learning, all the way to expertise. We ask our keynote speakers that they have an hour and a half each morning. We have one to start from the ground and to take us all the way to what is cutting edge. And then we have half an hour for questions and discussions. So it's very educational. We have a lot of participation, typically from students and postdocs. So I'm looking forward to seeing what are the latest things in AI. We have people from computer science and from math and from physics. But I'm also looking forward to seeing what the engagement of new people is and how much they can make of this educational opportunity and keep learning how to make it better, of course.
I'm looking forward to hearing what comes out of it. I always love seeing, the accomplishments that are made. And so I really appreciate you taking the time to join me today here on the podcast. Cecilia, thank you so much.
Thank you, Celia. It was a pleasure.